Okay, hello everyone. So today we will learn about vectors. So the learning objective for today is to define vectors, and then second, to solve vector operations, to express vectors as linear combinations of I and j, to recognize vectors in elementary kinematics such as acceleration and velocity, and then lastly to apply vector in real life. Okay, so what is vectors? Vectors is used to indicate a quantity such as displacement or velocity or force that has both magnitude and direction. So if you look at this, so we have, like, let's say this one is one vector. So we have this one, it points toward up and to the right. So this one is the direction, and then the length of it is magnitude. Okay, so vector we have from tail to the head, and it gives the direction. Okay, a vector is often represented by an arrow or directed line segment. So the length of the arrow represents the magnitude, and the arrow points in the direction of the vector. So a vector is represented by letter in boldface. So let's say we use boldface like this, V, or by putting an arrow above the letter. So we can also write like this. So we have the arrow above the letter. So a particle moves along a line segment from A to point B. So the corresponding displacement vector V has initial point A. So the initial point is called the tail, and terminal point B. So the terminal point we call the head. And we indicate this by writing. So let's say we have the A initial point to B. So we have this direction. So we can indicate the vector B as AB and then put the arrow on top of AB. Okay, and then let's say we have another vector U, where U is from this point C to D. So we also have this one, CD, and then on top we will put arrow. And then this U has the same length and the same direction as V, even though it is in a different position. So if you look at this, both have the same length and same direction. And then since these two have the same length and same direction, so we can say these two vectors are the same. So same magnitude. So the length of both vectors is the same. So as vector AB and vector CD, so we can say these two have the same magnitude and then same direction. So if the vectors point in the same direction, then they are parallel. So these two point in the same direction, so we can say that these two vectors are parallel. And then equality. So two vectors are equal if and only if they have the same magnitude and direction. So these two vectors, we can say these two vectors are equal. They have the same magnitude and the same direction. So combining vectors. So a particle moves from A to B. So its displacement vector is AB. So this one, A to B. And then the particle change direction and move from B to C with displacement vector BC. So this one from A to B, and then the vector change from B to C. And then we can combine this effect of this displacement that the particle now move actually from A to C. So A to B and then B to C, actually the vector move from A to C. So the initial point is A and then the final point is C. So the resulting displacement vector AC is called the sum of AB and BC. And we can write as this one. So vector AC is equals to vector AB plus vector BC. So in general, if we start with vectors U and V, we first move so that its tail coincides with the head of the other vector and define the sum of the vectors as follow. So let's say if U and V are vectors, position so that the initial point V, so let's say this one is the initial point of V, over here, is at the terminal point of U. So let's say we have another point, this one is the U. So this point here is actually the initial point of V and also the terminal point of U. Then the sum U plus V is the vector from the initial point U to the terminal point V. So we have this one. So this one is the U plus V, vector U plus V. So next we will look at the triangle law and parallelogram law. So the definition of vector addition is sometimes called the triangle law or parallelogram law. So this is the triangle law. So let's say we have U in this direction from here to here, and then we also have V from here to here. So we can add these two, we get vector U plus V, which is this direction. So then this one, we get a triangle shape. So that's why we call this one a triangle law. And then for parallelogram law, we do the same. So let's say we have this U, and then we have this vector V, and then the U plus V. So this vector V, we can shift to here so that the initial point of V is actually the same as terminal point of U. So we shift here, so we get this vector V, and then when we add, we get this. Also actually this U, we can also shift this U here towards this, so we get the vector U here. So V plus U also have the same vector as U plus V. So this is why we call as parallelogram law, because the shape here is we get parallelogram, and this one is actually where we can use to prove U plus V is equals to V plus U using parallelogram law. Okay, let's look at example. So draw the sum of the vectors shown in the figure. So we want to add these two. So we have vector A and then vector B. So we want A plus B. So we can draw A. So it should have the same length and also the same direction. And then at this terminal point of A, we draw vector B. So B, we have something like this. And then we can combine, so from initial point of A to final point of B. So we get like this. So this is vector A plus B. Okay, next we will look at scalar multiplication. So if C is a scalar or some constant value and V is a vector, then the scalar multiple CV, C times vector V, is the vector whose length or magnitude is absolute value of C times the length of V, and whose direction is the same as V if C is positive and is opposite to vector V if C is negative. And then if C is equals to 0 or vector V is equals to 0, then C times V equals to 0. So let's look at figure here. So let's say this one is our vector V. And then let's say we want to times 2. So 2 is positive. So the magnitude of V will be double of this length V. So that's why we have this one, the 2 times V. So the length will be double. And the direction is pointing towards the same direction as vector V because 2 is positive. Okay, let's say now we want to times negative 2. So now C equals to negative 2. So if you look at this, the absolute value of C equals to 2. So that's why the length of vector negative 2V is still the same as this one, which is double the length of vector V. But now the direction is actually pointing the opposite direction of vector V. So that's why we have this one towards the opposite direction. Okay, and then let's say we want C equals to 0 now. So V times 0, so we get 0 vector, the vector is 0 vector. So the magnitude is 0 and there is no direction. So no magnitude and no direction. That is what we call as 0 vector. So just now we look at when we combine or when we add two vectors. Now we will look at when we minus or difference of the two vectors. So two non-zero vectors are parallel if they are scalar multiples of one another. So this one is like, just now we can see everything. So since all of these are scalar multiples, so you can see that all of these are parallel. Okay, and then in particular, the vector negative v is actually we can split equals to negative 1 times vector v. So now the c equals to negative 1. So if you look at this, so if absolute value of c will be equals to 1, so the length of negative v will be the same as vector v, but the direction will be pointing towards opposite direction because c is negative. So this one we call this as negative of vector v. So the difference of two vectors, let's say we want to calculate u minus v, is actually equals to u plus negative v. So we can look at it the same way as adding two vectors, but now it's just that another vectors, we just put the negative sign in front of it, which make the direction the opposite direction. So this one, for example, we have this u, the direction is towards here, and then we have the v, so this is the direction of v. So if you want to do u minus v, so we start from u, and then for vector v, we will do negative v. So the direction of v is pointing towards here, so the negative v will be this direction. So this one will be the initial and this one is the final. So this vector we can put at the end of the final point of view. So we can put here. This one is the vector negative v. So then u plus negative v is this one. You get this one. So this is the vector of u plus negative v or u minus v, which is this vector. Okay. Okay, so let's look at one example. So we have vector a and b. So now we want to draw a minus 2b. So the b now, we want to times negative 2. So let's times 2 first. So times 2 means that it points toward the same direction. Okay. Points toward the same direction, but the magnitude is going to be double. Okay, so this one is the 2b. So now we want to make it negative 2b. So now the direction will be opposite, like this. So this one is negative 2b. So we have this one, the a. This one is the a. Oh. And then at the end of this, we add the negative 2b. So we have something like this. So this one is the negative 2b. Then we can combine these two from the initial point of A to the terminal point of V. So this one is A minus 2B. Okay, next we will look at components of vector. So if we place the initial point of a vector A at the origin, the 0, 0 of a rectangular coordinate system, then the terminal point of A has coordinates of the form A1, A2 for a two-dimensional coordinate system. So we can see in this figure. So we have this vector A. So the initial point here, we put the initial point at the origin, 0, 0. So this A will have the coordinate A1, A2. So this coordinate is called components of A and can be written as this. A equals to this one, A1, A2. And for component of vector, we use this symbol here, like this. Okay? Or this one, since this one is the X and Y coordinate, so this one also we can write as X, Y, like this. Okay, and then let's say, so this one we have A, we move the initial point A at the origin. So let's say we have a vector like this, where the initial point of this vector is at point x1, y1, and the final point of this vector is at point x2, y2. So for this vector, we can also write the components of this vector. So let's say this one is vector B. So the component of this vector is actually, the first component will be the x displacement of this vector, which is x2 minus x1. So this one, x2 minus x1 for the first component. And then the second component of this vector B will be the y displacement or the vertical displacement, which is y2 minus y1. So once we write like this, is actually we are shift this vector towards the origin, the initial point of this vector towards the origin. Okay, next we will look at magnitude or length of a vector. So a vector has the length which is denoted by the symbol, this symbol. We use one vertical line like this, or we can also use two vertical lines like this. So this one is actually the magnitude or the length. Okay, so the distance formula is used to compute the length of two-dimensional vector A, which has the component A1, A2. So the magnitude of A is equals to square root of A1 squared plus A2 squared. Or if this one is the x, y coordinate, so this one equals to square root of x squared plus y squared. So we use the distance formula because we want to find this length. So the x displacement squared and then plus the y displacement squared and then square root. So now we can, so given a magnitude and an angle, we can find components of vector. So a vector A with a magnitude this one, and the direction of vector A is at angle theta from the x-axis as shown in this figure. So let's say we have this vector A, and then from the x-axis to vector A, the angle here is theta. So we can find the x and y component of this vector A by using this formula. So the x component, which is A1, equals to the magnitude of A cos theta, and then the y component of vector A is equals to A2. The value for A2 is actually the magnitude of A sin theta. So this one, if you remember the trigonometry, we have this formula. So we have the sin theta equals to y over r, and then we also have cos theta equals to x over r. And r, if we bring to the left side, so we have y equals to r sin theta, and then this one is x equals to r cos theta. And the theta is actually the angle between the line to the x-axis, and r is actually the length of this. So this is where we get this formula actually. So the length of this r is actually equals to the magnitude of A. So the x equals to r cos theta, y equals to r sin theta. Or this one we can replace with magnitude of A. Okay, and then to find this component, x and y component of a vector, so the same thing for trigonometry. So this one we have to be careful with the quadrant. So let's say if it's first quadrant, then all will be positive. But if it is in the second quadrant, so let's say we have this vector B here, and then the angle here is alpha. So this angle is actually the reference angle. Okay, and then for this one, only the sign is positive. So that means the cos and tangent will be negative. So the x value here, which is cos, will be negative value. So this one, if the direction towards positive x is positive and the direction towards positive y is positive. So that means the direction towards the negative will be negative x will be negative and negative y will be negative. So in vector, the direction will be very important. That's why we have to identify which one is positive and which one is negative. So now we want to add vectors using the component. So let's say we have A, where the component of A is A1, A2, and B, the component of vector B is B1, B2. Then vector A plus vector B is equals to, so the component of the first component of A and B, we add these two components. So that's why we get A1 plus B1 and comma, and then we add the second component A2 plus B2. So basically, if you look at this one, vector A, so this one is the x displacement and this one is the y displacement. And then we have vector B, which is the x displacement is B1 and the y displacement is B2. So if we add these two vectors, we get this vector, where this vector is actually the A1 plus B1, the component for horizontal component, and then the vertical component or the second component will be A2 plus B2. So that's why we get this. So basically, we just add the components by components. And then if we want to multiply the vector by scalar, so let's say A, we have component of A, A1, A2, and C is a scalar or some constant value. Then C times A equals to C times A1 for the first component, and the second component is C times A2. So we will have like this. So this one is A, and then this one is the vector C times A. So the length will be different, will be depends on the value of C, and the direction will be the same. So these are the properties of vectors. So if A, B, C are vectors, and then C and D are scalars of some constant value, then we have, so the first properties is A plus B equals to B plus C. So this one we already know from the parallelogram law just now. And then the next one is, if we add B plus C first, and then we add A, this one is equals to, if we add A plus B first, and then we add C. Okay, and then the third one is vector A plus vector 0 or 0 vector is equals to A, because 0 vector is like there is no magnitude and no direction, so it's just equals to A. So this one is A, and then add 0 vector here is just A. Okay, and then A plus negative A equals to 0. So this one is A, and then plus negative A like this. So the initial point and final point will be the same. So that means there is no magnitude and also no direction. That's why we get the 0 vector. So 0 vector here is actually the component is 0, 0. So there's no magnitude and no direction. Okay, and then if some scalar c times vector a plus b, this one is equals to c times a plus c times b. Okay, and then if two scalars, so c plus d times a, so this one equals to c times a plus d times a. And then c times d times vector a, so this one is equals to c times d times vector a. And then 1 times a equals to 1. Since the scalar, the constant scalar is 1, so basically the magnitude will be the same and the direction is the same. So that's why we get A. So let's look at example. So determine whether or not the vector u from 2, 6 to 7, 18 is equivalent to vector v from minus 1, 4 to 4, 15. And then calculate the length of u. So we know just now if equivalent means it will have the same direction and the same magnitude. Or another way we can, so whether we can find the magnitude of these two vectors and also the direction of these two vectors. If these two are the same, then these two vectors are equivalent. Or another way is we can find the component of these two vectors. So this is where we have the x1, y1, the initial point, and then we have the x2, y2, the final point of vectors. So to find the component of these vectors, so for vector u, it's actually the final minus initial. So you find the displacement. So x displacement and the y displacement. So the first component will be 7 minus 2. So this minus this. And then the second component will be 18 minus 6. So we get the component for u is 5, 12. And then for vector v, we can also find the component for vector v. So the first component will be 4 minus negative 1. And the second component will be 15 minus 4. So we get vector v equals to 5, 11. So if you look at these two components of vectors are not the same. Hence, we can conclude that these are not equivalent. Or we can also draw in the xy plane. So vector u is 5, 12. So let's say this one is 5, 12. So the initial point is at the origin. So we have this one. So this one is the vector u. And then we have another vector v, which is 5, 11. So 11 here. So 5, 11. So initial point will be origin. So this one is the v. So from this, we can see that their direction is not the same. Hence, it is not equivalent. And then calculate the length of u. So since we already find the components of u, so we can calculate the length of u or the magnitude of u, which is equals to square root of x squared plus y squared, which is 5 squared plus 12 squared. So this one is equals to 13. Okay, let's look at another example. So if a equals to 4, 0 and vector b equals to negative 2, 1, find magnitude of a and then vectors a plus b, a minus b, 3b to a plus 5b. So let's first find the magnitude of A. So magnitude of A equals to square root of x squared plus y squared. So square root of 4 squared plus 0 squared. So we get 4. And then we can find vector A plus B. So this one, we add component by component. So this one, the first component will be 4 plus negative 2. And the second component will be 0 plus 1. So this one we get 2, 1. And then next one is A minus B. So this one is equals to 4 minus negative 2. And then 0 minus 1. This one equals to 6 negative 1. And then 3b. So 3b means that 3 and then times negative 2, 1. So this one is like 3 times negative 2, which is negative 6. So it's just multiplied by scalar. So my negative 6 and then 3. And then lastly, 2a plus 5b. So this one is 2 times 4, 0 plus 5 times negative 2, 1. So this one is 8, 0 plus negative 10, 5. And then we can add component by component. So 8 plus negative 10, we get negative 2. And then 0 plus 5, we get 5. Okay, just now we write the component in this form. So let's say we have A, we write the component in this form, A1, A2. So we use this symbol. So now we want to express the components of vector in terms of I and j. So in mathematical notations, the unit vector along the x-axis is represented by I, where I is equals to 1, 0. So basically the x value is 1 and the y value is 0. So we get this one. So basically if we have this one, the xy coordinate here. So the vector I is actually, let's say this one is 1, is this vector. So this one is vector I. Okay, and then the unit vector along the y-axis is represented by j, where j equals to 0, 1. So now the x component is 0 and the y component is 1. So let's say over here is 1. So this vector is j. Okay, 0, 0, 1. So any vector A, which has the component A1, A2, can be represented in terms of ij. So let's say A1, A2, we can split to be like A0 plus 0A. And then we can, this constant A1, A10 plus 0A1. So the constant A1 and A2, we can put it outside of this vector component. So that's why we have this one, A1 and then times vector 1, 0 plus A2 times vector 0, 1. And then we know vector 1, 0 is I and then vector 0, 1 is j. So we can write this as A1I plus A2j. So basically the first component will be together with I and then the second component will be together with j. So this one is equals to A1I plus A2j. Whenever we have this component, we can write as this. Okay. So if A equals to I plus 2j and B equals to 4i, express the vector 2a plus 3b in terms of I and j. So we can do, we want to find 2a plus 3b. So this one equals to 2. And then a equals to I plus 2j plus 3 times b. So b equals to 4i. So this one we can just expand the bracket here. So this one is 2i plus 4j, and then plus this one is 12i. Okay, and then we can add the same term together. So the I, we can add the i's together and then the j's together. So we have 2i and 12i. So this one becomes 14i plus 4j. You can also try to check whether this answer is correct using the vector component. So let's say we can write a equals to 1, 2 like this, the vector component, and then the b equals to 4, 0. So then we want 2a and 3b. So 2a equals to 2, 4, and then 3b equals to 12, 0. So 2a plus 3b equals to 2 plus 12, and then 4 plus 0, which is equals to 14, 4, which is the same as this answer. So the next we will look at unit vector. So a unit vector is a vector whose length is equals to 1. So the magnitude of the vector will be equals to 1. For instance, I and j are unit vectors because the length of the magnitude is equals to 1. And then in general, if magnitude of A is not equals to 0, then the unit vector that has the same direction as A is this one. So we can find for any vector A, the unit vector of A using this. So first we find the magnitude of A, and then the vector A divided by the magnitude of A to get the unit vector. So one example, find the unit vector in the direction of the vector 2i minus j. So let's say we have A, vector A is the 2i minus j, or in the vector component, this one is 2, negative 1. So first, we find the magnitude of A. So magnitude of A equals to square root of x squared plus y squared. So square root of 2 squared plus negative 1 squared. So this one equals to square root 5. Okay, and then the unit vector is equals to the vector A divided by the magnitude of A. So vector A is 2i minus j, and then divide by square root 5. So this one equals to 2 third 5 I minus 1 third 5 j. So this is the unit vector of U. And then you can check whether these are true, these are correct, the unit vector, by finding the norm of U, the magnitude of U. So the magnitude of U will be equals to 1 for this one. Okay, next we will learn about the dot product. Okay, so let's say we have A with components A1, A2, and then we have vector B with components B1, B2. Then the dot product of A and B is the numbers we can write as A dot B given by this. So A dot B is equals to the first component, we multiply the first component together, A1 times B1, and then plus, we multiply second component together, A2 times B2. So we have this one. So this one is the dot product. A1 times B1 plus A2 times B2. So let's look at this. So let's try this. So we have 2, 4, dot product with 3, negative 1. So this one is equals to 2 times 3 and then plus 4 times negative 1. So this one is equals to 2 and then B is negative 1, 7 dot product with 6, 2. So we get negative 1 times 6 and then plus the second component 7 times 2. So this one we get negative 6 plus 14, so we get 8. So the third one we have I plus 2j and then third product with 2j. So this one the component is actually 1, 2 and then the product with this component is 0, 2. So 1 times 0 plus 2 times 2. So the answer is 4. Okay, these are properties of the dot product. So the first one is, okay, if A, B, C are vectors and C is a scalar or some constant, then A dot A is equals to magnitude of A to the power of 2. Magnitude of A squared. So this one we can look at like this. So A dot A is equals to the first component of A, we multiply together, so we get A1 times A1. And then plus, we multiply together the second component, which is, B, it should be A2 times A2. And then this one is equals to A1 squared plus A2 squared, which is equals to the magnitude of A square. Okay, and then the second properties is A dot B is equals to B dot A. Okay, and then the third properties is A dot bracket B plus C is equals to A dot B plus A dot C. And then the fourth properties is we have some scalar C times vector A, and then this one we dot with vector B. This one is the same as we do the dot product first, A dot B, and then multiply with the scalar C, or the C is multiplied with B, and then we do the dot product, A dot CB. It's the same, these three. Okay, and then the last properties is if we have 0 vectors and then dot with A, we get value 0. This one is because the 0 vector is actually 0, 0. And then vector A is, the component for A is A1, A2. So if we dot these two, 0 dot A is actually equals to 0 times A1 and then plus 0 times A2, which is equals to 0. Value 0. It's not vector anymore. So basically, when we do dot product of two vectors, we get a number, a value. It's not vector anymore. Okay, angle between two vectors. Okay, let's say we have this vector A and then this vector B. So if you look at this vector A and B, so the initial point is the same over here. And then we can have angle between these two vectors, which is theta here. So if theta is the angle between the vectors A and B, such as in this diagram, then A dot B is equals to magnitude of A times magnitude of B cos theta. So this is the theorem. Okay, so this one is true. Then, actually if theta is the angle between vectors A and B, then we can have this formula. So this magnitude we can bring to the left side. So we can have cos theta equals to A dot B divided by magnitude of A times magnitude of B. So basically these two equations are the same, from the same equations actually. Okay, and then two vectors A and B are orthogonal or perpendicular 90 degrees. If and only if A dot B equals to 0. So the two non-zero vectors A and B are called perpendicular or orthogonal if the angle between them is pi over 2. So let's say we have this one is vector A, and then this one is vector B, and then the angle between them is pi over 2 or 90 degree. Okay, and then we can do the dot product. So we know the dot product A dot B is equal to magnitude of A times magnitude of B, and then cos theta or cos pi over 2. And then cos pi over 2, this one is actually equals to 0. So that's why we get A dot B equals to 0. So that's why if A and B, if A dot B equals to 0, then that means A and B are perpendicular or orthogonal vectors. So the angle between these two vectors will be 90 degree. Okay, let's look at example. So if the vectors A and B have length 4 and 6, so this one is the magnitude of A, this one is the magnitude of B, and the angle between them is pi over 3, so this one is the theta. Find A dot B. So we know from the formula A dot B equals to magnitude of A times magnitude of B, and then cos theta. So this one is equals to 4 times 6 times cos pi over 3. So this one equals to 12. So A dot B equals to 12. Find the angle between the vectors A, which is 2, 2, and then vector B, which is 5, negative 3. So we want to find the angle. So we can use the formula, the cos theta equals to A dot B divided by magnitude of A times magnitude of B. So from this, first we find the A dot B, and then we can find the magnitude of A and magnitude of B. So A dot B equals to 2, this one, 2 times 5, and then plus 2 times negative 3. So we get 10 minus 6, which is equals to 4. And then we can find the magnitude of A and magnitude of B. So magnitude of A is equals to square root of 2 squared plus 2 squared, which is 8. And then magnitude of B equals to square root of 5 squared plus negative 3 squared, which is equals to 34. Okay, and then we can use this formula, cos theta equals to A dot B, which is 4, and then divide by 8 times 34. So then we get cos theta equals to 0.2425. So theta equals to cos inverse of 0.2425. So we get 75.9638 degree. The next example is show that vector 2i plus j is perpendicular to vector 5i minus 10j. So to show that this one is perpendicular, then we can find the dot product. If the dot product A dot B equals to 0, let's say this one is A, this one is vector B, then we already show that it is perpendicular. So let's find A dot B. So this one is equals to 2 times 5, and then plus 1 times negative 10. So we get 10 minus 10, which is equals to 0. Then we can say that these two vectors are perpendicular or orthogonal vectors. Okay, next we will look at application of vector. So one application of vector is in force. So in physics, vectors play an important role in the resolution of multiple forces into a single resultant force. So we have multiple force coming from many directions. So when we add all these force together, we get single resultant force. So the calculation of force, taking into account friction and other physical forces such as like gravity or tension, or dividing of a force into directional components. So an important concept is the force equilibrium. So force equilibrium states that for a body at rest, so that means the body is not moving, with external forces applied, so the sum of these forces in all directions must equals to 0. So this is what force equilibrium states. So let's look at example. So a 100-pound weight hangs from two wires as shown in the figure. So we have these two wires, T1 and T2. Find the tension forces T1 and T2 in both wires and the magnitude of the tensions. So first we want to find the vector T1 and T2, and then we need to find the magnitudes of T1 and T2. So these are the direction of T1 and T2. Okay, and then we have 100-pound weight hangs. So hangs means this weight is at stationary, or the body is at rest, does not move. So this is when we apply forces in equilibrium. So all force we add together must be equals to 0. So how to do this question? First, actually we can draw this in the XY plane. So let's say we have this one, we can draw like this. Okay, and then this one. So let's say this one is the X coordinate, and then this one is the Y coordinate. Okay. So if you look at this, we have the T1. So the initial point T1 is at the origin, and then the vector T2 also have the initial point at the origin. Okay. So that's why we draw this X and Y plane in this way to make it easier. So the angle here is 50. So this one, since this one is parallel to this axis, so that's why angle over here will be 50 degree. And then the same goes to this. Since this one is 32 and this one is parallel to this x-axis, so over here the angle will be 32. Okay, if you look at this, we have two forces, the T1 and T2, and actually we have another force. So we have the weight, which is 100 pounds. So this weight, the force will be going downwards like this. Okay, so this weight, so let's say we define the force here as W. So we can get the vector W. So vector W also have the initial point at the origin. So we can write the component of W. So the X component or the horizontal component will be 0. and the y component will be negative 100 because it's pointing towards the negative y direction. So we have negative 100. Okay, and then we have T1 and T2, force T1 and T2. So force T1, okay, this is when we use the trigonometric rule. Okay, so the T1 here is actually in the second quadrant. Okay, and then this one is, if you still remember, let's say I put here A, vector A. This one is equals to norm of A cos theta for the first component, and second component is norm of A sin theta. So this one is the x and y component. Okay, so the same goes for T1 and T2. So T1, the x component or the horizontal component, first component will be the norm of T1 and then cos theta, where theta here is 50. Okay, and then if you remember, this one is in second quadrant, so only sign is positive. So that means cos will be negative. Okay, and then the second component or the y component will be the norm of T1 sine 50, and sine is positive. Okay, and then the same goes for T2. So the first component will be the norm of T2 sine 32. So this one is in first quadrant. So sine cos tangent will be positive, and then second component will be norm of T2. Sorry, the first component will be sine. This one, the first component will be cos, and the second component will be sine 32. Okay, now we want to find T1 and T2. So basically, we already have the expression for T1 and T2, which is these two expressions. Okay, but now we have to find the magnitude of T1 and T2. So to find this, we need two equations, and to get the two equations, this is when we use the equilibrium force. So we know since this is at rest, so the total force must be equals to 0. So we have these three forces. So we must have T1 plus T2 plus W equals to 0. So that means we add all the x component must be equals to 0, and we add all the y component must be equals to 0. This is where we get the two equations. And from these two equations, we can solve to find T1 and T2. So let's add the first component. So we have negative norm of T1 cos 50, and then plus norm of T2 cos 32 plus 0 equals to 0. And then we can add the second, so this one is number 1, and then we can add the second component. So we have norm of T1 sine 50 plus norm of T2 sine 32, and then minus 100 equals to 0. So basically, if you look at this, these are actually two equations that we can solve simultaneously. So I leave it to you guys to solve it. I'll just give the final answer for norm of T1 and norm of T2. So when we solve, we get the norm of T1 is equals to 85.6403, and then norm of T2 is equals to 64.9154. So this we already find the magnitude of the tensions T1 and T2, and then we need to find the tension forces, the vector T1 and T2. So once we find this norm of T1 and T2, we can substitute back inside here, the one that we already defined. So when we substitute back, we can get the vector T1 and T2. So the vector T1 is equals to negative 55.0485, and then the second component is 65.6043. And then for vector 2, the first component is 05.0514, and the second component is 34.3999. So you can try whether you get the same answer as mine or not. Okay, another application for vector is actually the resultant velocity. So this is an example for resultant velocity. So a plane flying due east at 200 km per hour encounters a 40 km per hour wind blowing in the northeast direction. So the resultant velocity of the plane is the vector sum v1 plus v2. Okay, where v1 is the velocity of vector of the plane and v2 is the velocity vector of the wind. Okay, let's try draw this one. So let's say we have this. We can draw like the xy plane, or we can draw like this one is the east, north, and then west, south. So a plane flying due east. So the plane is flying towards east direction. So let's say this one is the plane. So the velocity vector of the plane is this direction. So let's say this one is v1. Okay, and then we have, okay, so and then the speed is 200 km per hour. So that means the norm of v1 is equals to 200. Okay, and then we have the wind blowing in the northeast direction. So let's say the northeast direction is this one, this way. So the velocity vector for the wind is v2, is this one, with the magnitude of v2 is equals to 40 km. So basically this one is the direction of the plane, but then we also have the wind. So basically the resultant velocity is actually v1 plus v2. So if we add these two, v1 plus v2, let's say v1, and then we want to add v2 like this. So we get the, this one is the resultant velocity v. Okay. So this one is another application of vector, resultant velocity. So for this one, the angle between v1 and v2 is pi over 4. So the angle is actually this angle, pi over 4. And then determine the resultant speed of the plane. So basically we want the speed, or we want the magnitude of v. So to do this, first we can find the resultant velocity v, the component of v. So we know v is equals to v1 plus v2 . So to find the component vector of v, first we have to find the component vector of v1 and v2. So v1, the component vector of v1. So since v1 is in the direction is towards east or towards positive x-axis, so we have only the value for the horizontal value. So the first component will be 200 and second component, which is the y value, will be 0. So this one is for V1. And then for V2, so the first component will be norm of V2 cos 45 degree, and then second component will be norm of V2 sine 45 degree. And then norm of V2 is 40. So this one is actually 40 cos 45 and then 40 sine 45 degree. And you guys can calculate this value actually. Okay, then now we already define the vector component for V1 and V2, and we can add these two components, these two vectors. So we have V equals to, so we add the first component together. So we have the first component is 200 plus 40 cos 45, and then the second component is 0 plus 40 sine 45. So this one is actually equals to 200 plus 40 over sec 2, and then 40 for the second component is 40 over sec 2. So this one is the vector V, resultant velocity V, and then we want to find the norm of V. So the norm of V is equals to square root of x squared plus y squared, or the square root, so square root of 200 plus 40 over sec 2 squared, and then plus 40 over sec 2 squared. So when we solve this one, we get the magnitude here is equals to 230.0298 kilometer per hour. Okay, let's look at one last example. So a guide wire is used to stabilize a power line pole. So we have this one power line pole here, this one pole. So the pole here is actually 10 meter, the height. Find the proper position x. So we want this one, the value of x here. To place the wire, so the wire has vector A. If the wire can provide 600 Newton force, so that means the magnitude of A here equals to 600 Newton, and the force F due to the power line is 500 Newton. The direction of F is this way, and the magnitude of F is equals to 500 Newton. By examining the components of F along A and pole P, and then calculate the force along the pole P. So first we want to find the position X, and then second we want to find the force along pole P. So for this one, again, we can draw in the XY coordinate. So let's draw in this one. So first we have this force. Okay, so let's draw the force. The initial point will be at the origin, so we have this force. and then the magnitude of F equals to 500. Okay, and then second force will be wire A, the vector A, and then the vector A, this one is the tension. So basically the vector A, the direction will be like this. So if you want to draw this one, this vector A, so the initial will be at the origin, so we can draw. We can draw this vector A like this. If the angle here is theta, and then again, if we draw over here, the angle here will be theta. So the same thing, the angle here will be theta. Okay, and then magnitude of A equals to 600. Okay, so basically, we have these two forces to hold the pole in place. And then since the pole is in place at rest, so that means total force will be equals to 0. Okay, so we also use the force equilibrium. So F plus A is equals to 0. So we have this. So now first we have to identify the vector component for F and also the vector component for A. So the vector component for F, so since it has only the horizontal component, so the horizontal component will be negative 500 because it points towards the negative x-axis, and then the y component will be 0. And then for vector A, so this one is in fourth quadrant, so the cos will be positive. So this one will be the magnitude of A, which is 600, and then cos theta, and then the second component or the y component will be negative 600 cos theta. So basically, if we can draw, so the A here, if we split into the two components, we have actually this one. So this one is the horizontal component, or the first component, which is 600 cos theta, and then the second component is this one, point downwards. So this one we have negative 600 cos theta. So the question asks about the value of x, and then second asks about the force along the pole P. So basically the force along the pole P is actually this value, the 600 cos theta. So we want the magnitude of this 600 cos theta. So first we have to find the x. So to find x, we use F plus A equals to 0, the total force equals to 0. So we can add the two components. So let's say we add the x component. So we have negative 500 plus cos theta plus 600 cos theta. Oh, I don't know why. So we add the x component, so negative 500 and then plus 600 cos theta and then equals to 0. So from here we can solve 600 cos theta equals to 500. So cos theta equals to 500 divided by 600, which is 0.8332. And then we can solve for theta. So theta equals to cos inverse of this, which is equals to 33 degree, 33.5573 degree. Then once we have this theta, then we can use this to find x, value of x. So if you still remember the trigonometry, so we have this formula for tangent. So tangent theta is equals to y over x. So if you look at this figure here, we already have the y value, which is 10 meter, and we want to find the x. And then we also have the theta here. So we can find the x. So x is equals to y divided by tangent theta. So x is equals to 10 divided by tangent 33.5573. So then we can find x is equals to 15.0756 meter. So now we find x. Next we want to find the force along P. So basically the force along P is actually this one, this value, the 600 cos theta. So the force here is this one is actually 600 cos theta, which is equals to 600 cos 33.5573, which is equals to 331.6624 Newton. Okay, I think that's all for today. Okay, thank you everyone.